My name is Jeff Shapiro. I'm the director of MIT's Research Laboratory of Electronics, and it's my pleasure to welcome you here today to a special RLE seminar. Our speaker is Professor Peter Hagelstein. Peter had his undergraduate and graduate education here at MIT. He did a doctoral thesis on the design of short-wavelength lasers, and then went on to the Lawrence Livermore Laboratory, where he did some very fundamental work leading to X-ray laser operation, and returned to the MIT faculty, where he's worked on a variety of issues, including quantum soliton propagation in fiber, and recently work on a new approach to thermionic electric power generation. And he's also spent a great deal of time worrying about anomalous effects in metal deuterides. And it's this latter topic that he's going to speak to us today about. Peter.
I gave this talk at Berkeley on invitation from the Nuclear Engineering Department September 30th. And there were some hard-nosed senior folks from the physics department there, nuclear types. And they seemed to be pleased with it. And I thought, wow, that's odd. So I thought I'd give a version of the same talk here at MIT. In part for some of my friends and colleagues who've been curious about what I've been up to all this time. And I thought, well, I've gotten to the point where I think I know something, so raise the flag and see who salutes. In 1989, as many of us remember, the announcement of some effects, an excess heat effect in palladium electrolysis and low-level DD fusion from titanium cathodes. These claims were rejected in short order. The technical reasons for it, one is that screening was insufficient to allow two deuterons to get together in order to fuse, even at the rate which Jones claimed that he saw fusion neutrons from. In addition, if there's, for the excess heat claim, if there was going to be any near reaction, it would have to be faster than the normal DD fusion reactions, which happen as fast as they can. Two deuterons come together. The final state products leave about as fast as nuclei with that much energy are capable of moving. And it was thought that there couldn't be anything that could happen faster than that, because that would have to imply things were moving much faster than laws of physics would allow. In addition, normally exothermic nuclear reactions give energetic particles out as final products. The primary claim that Fleischmann made was that he was getting energy without energetic particles. The basic claims are inconsistent with, or are inconsistent with the main body of nuclear physics as accumulated over 60 years. In addition, there was difficulties replicating experiment in other laboratories. The arguments against this were not convincing to everybody. Initially, perhaps 500 or 1,000 scientists worldwide kept on working. Some of the reasons that the arguments weren't convincing was, given that the most important claim was heat without energetic reaction products, one of the primary criticisms of the claims was that there was heat without reaction products, and that's unsettling. Namely, if the fundamental claim implies a new mechanism, then the discussion should concern the new mechanism rather than the absence of reaction products. Another fundamental reason for rejection was the notion that there was no possibility that you could have physical processes to work that way, and yet the arguments that were given as to why there could be no reaction processes that work that way, there was no proof of any sort. It was given as assertions. So that sort of means that you can find reaction mechanisms that work that way, and that invalidates the primary criticisms as to why these things should be rejected. And so forth. Reproducibility issues often have to do with how well you know what you're doing in the lab. And dismissal to clarification experimentally, and experimentally didn't seem to me quite to be appropriate. Before 1989, question of motivation. Why would someone perform such experiments in the first place? A lot was said in 1989. Everybody remembers what was said. I spent some time, I cornered Fleischmann. I said, well, why in the world did you do these experiments in the first place? And what Fleischmann says was that in the 60s, or actually he said that electrochemists have long been aware of problems with the calorimetry of palladium deuteride, palladium hydride. And the issue is that when people would do calorimetry on palladium hydride, typically the accuracy could be very high, 1/10% or thereabouts, and it would work every single time. However, when the same electrochemists would do calorimetry on palladium deuteride, there would inevitably be small discrepancies in calorimetry, small being on the order of 1% or 2. And typically it would be in excess. So Fleischmann argued that the electrochemical community had long known that there were difficulties in palladium deuteride versus palladium hydride. Now the electrochemists I talked to it wasn't well known to them, but presumably there existed some electrochemist somewhere that it was well known to. So as a result, if this is actually right, because Fleischmann says one thing one day and another thing another day, so one can never know. But perhaps this makes things more understandable. But the initial Fleischmann attempt might be viewed as an effort to follow up on some subtle calorimetric effect that had been observed previously, as opposed to Fleischmann's rationalization, his attempt to come up with a theory, which at the time was that so many deuterons were going to lattice, they were being crushed at a density more than that at the center of the sun. 2002, 13 years later, we've got a different situation. Several hundred scientists several hundred scientists initially continued looking at the problem. There's about 150 left total worldwide in this day and age. Support's problematic for most. There's been 9 international conferences. Roughly 3,000 manuscripts have been written. I will be the first to admit that of all these 3,000 manuscripts, not all of them are overly helpful. There are some publications in referee journals. The most important work appears in the conference proceedings for these conferences. And this work is being done against the most severe opposition in the scientific community. And that translates into you work on it, your career doesn't advance, your papers don't get accepted, and you don't get funding. There has been some clarification over the years. There's been replication of the excess heat effect many times in laboratories. There's been experimental response to most of the criticisms raised in 1989. Excess heat with closed cell calorimetry has been observed in excess of 50 sigma. Improvement in reproducibility of anomalies. Some of the anomalies can be observed at the 50% reproducibility level or so in the best of cases. There's now been a detection of the ash associated with the excess heat, or at least a claim for the detection of the ash. And there's a new set of anomalies as well. One of the claims is for DD fusion products coming out of metal deuterides, including protons, tritons, neutrons, and helium-3. So my 3D graphics rendering of it pictorially. Some of the other reaction products, alpha particles have been claimed to have been observed up to 21 MeV, and that's not an easy thing to have happen. Tritons, gammas, mass 2-3 ejecta of 1 to 6 kilovolts. And the gammas, enough gammas came out of an experiment in Italy for Gozzi's team to image his cells through metal at 3 meters. Based on the absorption of the material that the gamma rays went through, it was estimated the gamma rays were centered centroid energy in the vicinity of 90 kilovolts. Induced radioactivity is, this experiment was the one which I think convinced me that there was something to all this. You might argue for all the other experiments we've got, tritium contamination, you can't measure temperature right, you can't do this, you can't do that. But Kevin Wolf had been studying neutron emission. He came to SRI at the encouragement of Everett, because his electrochemistry was very similar to Mike McCoubrey's with SRI. McCoubrey explained to him that he could put a surface colloid on by adding boron and silicates to coat the surface, which would allow the deuterium to go in, but inhibits gas formation on the way out to get higher loading. And he went back and he tried that, and during one of his runs, 3 of his cathodes became radioactive. The radioactivity was verified in a high-purity, high-efficiency germanium detector at Lawrence Livermore Laboratory. It was Kevin Wolf, who's not with us these days. This was a tremendously important experiment. Kevin was unable to replicate this experiment. I personally essayed more than 100 cathodes from different people's experiments looking for this gamma ray spectrum, and came up empty-handed. The identification of the isotopes goes as follows. There were roughly 100 gamma lines observed at 4 orders of magnitude above background. These isotopes were identified from the gamma lines, but it was preliminary identification. I think one of them is wrong. The half-life of these isotopes ranges from about 3.5 days, there's one at 4.3 days, up to several years. The amount of isotopes, Kevin had a record. He could see in the gamma rejection of the neutron detector when the radioactivity was induced, and he could work back to T=0 from a measurement of the amounts at different times, how much was the initial hit. And these are the numbers that he and his collaborator at Berkeley came up with. Total induced radioactivity corresponded to something like 10 joules of these numbers don't look like 10 joules. He was arguing something like 10 joules of induced radioactivity. The excess heat effect, claimed power densities are in the general range of 5 to 5 kilowatts per cubic centimeter. In some cases, it's likely to be a bulk effect. In other cases, likely to be a surface effect. In general, it's not particularly well understood where and how it happens. In the Kevin Wolf radioactivity, the radioactivity was peaked in the middle of the rod and was lower outside the rod, which was suggesting in that case it was a bulk effect. In other cases, it's rather clearly a surface effect. The total energy produced is, in many cases, is reported to be on the order of hundreds of electron volts per palladium nucleus. There are claims very much higher than that as well. The argument for the total amount of energy is such that you would not be able to account for it from a chemical process. The calorimetry, there's been lots of calorimetry done. At SRI, we did closed cell mass flow calorimetry. It's called first principles calorimetry. Probably can't see it, but water flows in, water flows out. The water flows all around the cell, and any energy from the cell goes into the water and can be detected through a knowledge of mass flow rate, the heat capacity, and the temperature difference, which is measured accurately. The SRI group was able to account for their best calorimetry, roughly 98.5 to 99% of the energy from things going on inside. The amount that they could not account for first principles calorimetry was done with Fick's law constant. The highest accuracy reached in this calorimetry is roughly 0.1%. In this data, the solid line is the current steps that are imposed. SRI found that when they changed the current, they would get a response from the cathodes. 2 cathodes were run in identical cells, one light water, one heavy water. The heavy water one went up in connection with the current. The light water one either didn't or didn't as much, depending on your point of view. And there are, at SRI, something in the neighborhood of 40 different examples of this kind of effect done in high accuracy closed cell calorimetry. There are many examples from other laboratories as well. There are many, the key experimental claims are low-level DD fusion, emission of non-fusion ejecta. There are a number of claims of transmutation. There's a recent paper in Japanese Journal of Applied Physics by Iwamura claiming a transmutation effect that was witnessed in real time. And which is, that effect is consistent with the material I'll be talking about later today. It's induced radioactivity, which even though it's not been seen since, it's not consistent with neutron activation, proton activation, alpha, or other particle bombardment. It's largest in the middle as opposed to the outside. It is consistent. Induced radioactivity, I've attempted to model it, and I can model with the approach that I'm doing and get the induced spectral radioactive particles pretty much within a factor of 2 for all except for 1. And the 1 may be a misidentification. NRL does not. NRL looked at it and didn't agree with the Wolf-Berkeley analysis on one of the isotopes. So excess heat effect. Helium has been observed in correlation with the excess energy. They measure the amount of energy, the amount of helium, divide, and they come up with a reaction Q value. The reaction Q value has been measured now in 6 different experiments. The best of the experiments gives a value of about 24 MeV, which is the DD go to helium-4 reaction energy to within about 10%. And tritium production has been claimed to have been observed in many times. Most recently, in a Fusion Science and Technology article, where the tritium was made from inside a hollowed out cathode that had black in it. Tritium diffused out of the cathode, decayed to helium-3, it left helium-3, and the helium-3 pattern shows a diffusion pattern out of the center magnet region. Talk about theoretical notions. Postulate. First theoretical postulate. Whatever is going on, DD fusion is at most a minor contribution to it. Namely, in 1989, the claim was that whatever was happening had to be DD fusion, didn't agree with DD fusion, and hence it wasn't real. Let me revise the postulate and say whatever it is that's happening, the primary effect is not DD fusion, at least as known by the nuclear physics community. Another postulate, which I owe to a number of my colleagues, is that in the end, whatever it is that might be going on has to look to be simple retrospectively, because if it isn't simple, it's wrong. Okay, where to start? Fleischmann's initial conjecture, before much was known about this at all, was that 2Ds were going to make helium-4, and 24 MeV was coming out in the form of heat. And at this point, the experiments appear to support this conjecture, although Fleischmann at the time just had no way of knowing. Now, from a atomic physics viewpoint, to get 2Ds to go to make helium-4, your microscopic angular momentum isn't right. You have to have an exchange of 2 units of angular momentum to make this work. So if there's any chance of this to work, you have to supply the angular momentum microscopically from somewhere. Normally in the vacuum, the angular momentum comes from emission of quadrupole electromagnetic quanta gamma ray. The conjecture here is that, the important conjecture here is that if you exchange a phonon can contribute angular momentum. And as a result, this appears to be a place to start, to imagine that 2 deuterons can fuse in a solid in combination with phonon exchange. So the theorem, this one's a theorem as opposed to a postulate. Phonon exchange can occur when 2 nuclei fuse in a lattice I looked up in the dictionary earlier today. Theorem is a statement which can be proven from known accepted theory facts. And in this case, this has the ranking of a theorem. I'm not sure anyone would disagree. Well, this was the place where I started in 1989. I said, suppose you have a quantum mechanical two-level system. You have a complex physical system. You're doing quantum model, and I replaced the complex quantum system with a simpler idealized system. So here's my simpler idealized system. There's an upper state which represents molecular D2 within the metal Deuteride. There's a ground state which represents helium-4. And there's an oscillator which represents the phonon modes in the lattice. The question is if you hook up a two-level system to an oscillator, what happens? Well, this is a problem that's been long studied in the physics literature. Basically, the picture of it is you have an oscillator, and I've added some broadening since phonons are lossy and oscillators wind down, so there's a line width associated with it. The two-level system may not be centered at the same frequency of the oscillator. There might be some mismatch. The phonons, for example, might be around 50 millivolts. The two-level nuclear system might be at 24 megavolts, so there's a little bit of a difference between them. The width, of course, of a phonon line is nowhere close to 24 megavolts on the second. However, the two-level system overlapping with the oscillator, the lines overlap, and then you can transfer energy as a first-order process. Now, I modeled it, and I very early on, in fact, in April of 1989, I proposed models of this sort to try to begin to understand how the coupling might work. And basically, what I found is that it doesn't work very well. The interaction's too weak from the molecular state. The off resonance is bad. Even if you have a very nonlinear interaction, there's just no way to get the energy in, so it's broken. I said, well, in those days and in these days, I said, well, suppose you have many sites interacting, two-level systems and many sites interacting with the photon field, the coupling might be stronger. Maybe that helps. And in 1989 and again 1998, I came back to this problem, and the answer is the coupling is very weak and just doesn't go. You've got this big quanta, the lattice one's small quanta. You've got $1 and your bubblegum machine takes pennies. Might not pennies anymore. But you try to shove your $1 into the bubblegum machine that wants pennies and it doesn't go. You try to shove the large quanta into an oscillator, it takes a small quanta, it just simply doesn't want to go. You got to chop up your dollar bill into pennies before you can make it work. So the only way around this at this level is the following argument. Suppose your phonon mode is here and it has some line width. Suppose your two-level system is out here, 24 MeV, 50 millivolts, large distance between them. The question is what's the line width look like out at 24 MeV? Okay, sounds like a weird question. You go to the literature and you flip through the books and you say, well, what's the response of the phonon mode at 24 MeV? Scratch your head and say, well, what a dumb question to ask. No, it's not been considered. Nobody's had any reason to consider what the response of a phonon mode would be at high frequency. Now, you can make some progress by thinking a little bit about the problem. Coupling between phonons and other phonons can give width to a phonon wire shape.
Yeah, if I can just interrupt when you say that no one has dealt with that issue. Actually, local phonons, very highly localized phonons, have been identified at that frequency, and we're very close to it, in palladium deuteride and palladium hydride in the context of the fact that that material becomes a relatively high temperature superconductor at so in other words, those modes have been, those phonons have been identified.
Certainly localized phonons have been identified, and I don't need to, indicate that the superconductivity and the work that you've done is not important.
No, I'm just stating an experimental fact that in the literature,
Certainly
not my
there's-
literature.
No,
but,
there's neutron scattering that's identified and observed. Neutrons banging against the deuterons, you can see both the center frequency, you can see the line shape as well. So where there's large response, you can see it in the neutron spectra directly. You might expect that the phonons could generate some line shape and response due to coupling with electrons. However, that's at the electron volt level, so you still got to get out to 24 MeV. So let me put a question mark here to be followed up shortly. Suppose the phonons happen to couple with nuclei, namely if your phonon node actually were coupled with the nuclear system, then if you drove the phonon node at a frequency which the nuclear system would respond, it could be thought of in terms of equivalent line shape. This initial thought was something I was using back around 1990 or so, and it's going to come up again shortly. Conjecture. Coupling between fusion reactions lattice possible. I'm going to bring up the discussion so far. If lattice nuclear coupling can give a admittedly small contribution to a phonon line shape in the MEV region. Okay, new physical mechanism. Basically, up to this point, the notion of two-level systems and oscillators, basically we largely ran out of steam. We're not going to get, from the analysis we've talked about so far, we're not going to get a lot of reaction, not going to be able to convert the power decently, and so forth. Now the reason for it is that the coupling is weak, the quantum is big, and the oscillator quantum is small, and so forth. So at some point, you've got to turn back to experiment. Scratch it and say, okay, experimentals show me something that will help me sort out mechanism. And the claim is that DD fusion by itself in the lattice Jones's observations, while it's nice, it doesn't tell you anything about mechanism. The Pons-Fleischmann claim of heat with no energetic reaction products excludes a lot of things, but it doesn't tell you anything positive. There's no positive statement in that about what's happening. So what I'm hoping for is to find an experiment that will tell me something positive that I can make a positive theoretical conjecture out of. There's an experiment that was reported by George Chambers, which at the time was the only observation of it, and the signal wasn't very strong and so forth. But George Chambers worked with a ECR source, electron cyclotron resonance deuteron beam, which had deuterons come in, deuteron ions, I believe, come into Poynting direct coil. Graham, correct me if I'm wrong, it's around 500 eV or so. Out of this was detected alphas at 18 to 21 MeV. Now, alphas at 18 to 21 MeV is a very energetic alpha. If you have alpha decay of radioactive nuclei, about the highest energies you get is about 5 or 6 MeV. And the more energy that you get, the faster the alpha tunnels through the barriers. So things with energetic alpha emission would have very fast decay. The observation of energetic alphas here are very unusual, very difficult to account for by any reaction mechanism. It's not a normal part of nuclear physics. If a deuteron comes in, even with a fast beam and hits something, you're unlikely to generate alphas at 21 MeV through normal two-body interactions. After thinking about this for a long time, the conjecture arose that you started out with two deuterons and you made helium-4. Two deuterons come together and makes helium-4 at one site. At another site, if you have phonon exchange, the phonon node might talk to your two deuterons and it might talk to a plating nucleus. You couple to the phonon node, exchange phonons, and then the phonon node couples to perhaps a palladium nucleus. And there's different palladium isotopes, but you generate reaction products in the range that George Chambers measured alphas at. So for example, if you take this and go further, if you consider ionization to the ground states of the nuclei only, you generate something between 19, basically 21 MeV. And if you were to include the fact that some of the final state nuclei would be in excited states, typically you get another MeV, a little bit more out of it. And so that would spread things between 21 and roughly 18 MeV, more or less in agreement with the measurement of Chambers. So this is from my perspective, this is the very first hint that the experiment actually contains information about a mechanism from which you might be able to learn something with a theoretical sample. To conjecture, the implication of the Chambers experiment is that mechanism exists for energy from reaction at one site to be expressed elsewhere. So this is important conjecture. Now, I've been working with my colleagues in the community to get me some more of these alphas so we could clarify things. And since that time, by now, there are currently roughly five experimental reports that appear to be consistent with this notion. Ed Cecil reported protons near 11 MeV from titanium, which is pretty close to what you'd expect from this reaction mechanism. Lipson and independently Carbu have seen fast alphas out of palladium deuteride and I believe titanium deuteride as well. So this appears not to be a flash in the pan. It appears to be something that can be seen in more than one laboratory. So conclusion is that we've got a new kind of reaction that we can begin thinking about, where a fusion at one site, a nucleus at another site, goes to a fused system at one site and a dissociated thing at another site. So this is a step forward, at least for me, theoretically. Okay, not shift gears. Let's take this notion and go further, because it implies that a different kind of reaction ought to be very much more important. Now, the initial idea was that for the Chambers experiment, two deuterons are going to come together, that perhaps there might be electromagnetic coupling to a nearby nucleus. You can calculate that coupling and find that it's exponentially damped manyfold before you even go a tenth of an angstrom. So the idea is that it can't possibly be electromagnetic coupling, and this notion of phonon exchange became important because a phonon can be an extended object. If you've got a highly excited phonon mode, then then all you require is that the fusion happen exchange more than one phonon with your excited phonon mode. Then you're coupling to another system somewhere else, ends up being hindered algebraically and can be non-local. The idea is that two deuterons come together at one site as one half of a second order reaction, exchanges phonons with the phonon node, and the phonon node has to couple both sites. And then at the second site, phonon exchange results in dissociation. So the overall second order reaction then conserves energy. One half or the other half of the second order reaction by itself does not conserve energy, but the second order process overall would be conservative. Now, I have modeled this, and I come up with a couple of conclusions. One conclusion is that in the case of a single highly excited optical phonon mode, coupling can be long range if you have nonlinear interaction with the phonon field. And these formulas, the infinite order Villon-Bigner, basically you've got your interaction, you have a non-resonant denominator. The moment you're dealing with one optical phonon mode, your non-resonant denominator decreases the interaction algebraically. If you had all phonons contributing on equal footing, you would find an destructive interference between all the modes and an exponential decay at the range with a very short distance. Now, the question is if you've argued that you have this site-other site mechanism, question is what's the dominant process? Which process happens faster than, which second order process happens faster than all the other second order processes? Well, in quantum mechanics, we've got a formula for reaction rates, and it cares about the interaction matrix elements squared, and it cares about the density of states. Now, the argument was that if you have a resonant reaction with a ground state, that the density of states could be very high. Namely, if you have chambers like dissociation, ionization reaction, the alpha goes into a continuum. So the density of states is very low because there's a wide range of states. If you had a resonant reaction, the density of states would be very high. By this argument, we could deduce that the resonant version, a reaction plus its inverse, where the final state is found, there's no continuum, and the process is resonant because you have the same thing on one side as you have on the other side. That process should be the fastest process. So the idea is two deuterons fuse at one site, exchange two or more phonons with a very highly excited optical phonon mode. The optical phonon exchanges two or more phonons with a helium-4 somewhere else, dissociates the helium-4, and the overall second order process is energy conservative, it's resonant, should have the highest possible rate. Of course, as a reaction, it's not the world's best reaction because you don't actually do anything. You have two deuterons helium-4 initially, you have two deuterons helium-4 after the fact. It's almost like they exchanged places or something. So even though theoretically this is supposed to be the dominant process, as a dominant process, it doesn't look very promising initially that you actually would ever be able to prove that this is the dominant process. However, now we can make conjecture that the dominant site, other site reaction is the null reaction within this way of thinking. Detection of null reaction. Okay. Can you detect it? If you could detect it, that would be spectacular, because then you could make further progress. Question: is the null reaction observable? Conclusion. Well, I don't actually believe that you can detect a helium and two deuterons within the submicron region difference under these conditions until that just two of them have exchanged. However, if a helium-4 dissociates through this kind of mechanism, the two deuterons are born close together. You might think, well, the link, right? Except that there's a Coulomb barrier that they have to tunnel through the lead, and the tunneling probability that's associated with the Coulomb barrier is very small. So the thing is if you actually do this, when the helium-4 dissociates, the two deuterons that are born, they're made from the dissociation, they're born close together, and they're escaping from one another is hindered by the Coulomb potential. Consequently, it seems maybe there's a break here such that we can do it. So the idea then is that if you come in with a projectile, and if the two deuterons having been created through phonon-induced second-order dissociation of helium-4, if they have to be close to one another, maybe you can hit them. And if you can hit them, you'll get a reaction. Because if the two deuterons come together, they'll make helium-4, you'll have 24 MeV. And 24 MeV on the nuclear scale is like a firecracker or something. It blows up, it makes things happen. And in principle, you ought to be able to see that. Theorem. The deuteron pair formed from resonant dissociation has a low probability of tunneling apart. Something could be proven, it can be proven, has been proven from conventional accepted quantum mechanics. Conjecture: the null reaction may be observable in a collision experiment through the observation of direct observation of deuteron pairs in a collision experiment. Namely, if you throw something very fast at a metal deuteride where there are compact DD states, or where deuterons are close together because they've just been dissociated, then you'll get a reaction, and then that will allow you to have eyes at this scale and be able to see that two deuterons have been created from a helium-4 in this way. This brings us to the Kosaki experiment. In 1995, Kosaki reported that in experiments where a 100 kilovolt deuteron beam hit titanium deuteride, he was actually studying DD reactions, trying to understand whether everything was happening sort of the way they were supposed to happen. And he had a large flux of deuterons coming into titanium deuteride, and he got a massive flux of conventional DD fusion reaction products coming out. In addition, he also saw some fast protons with energies up to 17 MeV and fast alphas up to 7 MeV. Now, by itself, fast protons and fast alphas are not unexpected in this experiment. For example, if you have helium-3 accumulating from the reactions in the first place, if the deuteron hits helium-3, you'll generate a 17 MeV proton. In addition, if a deuteron hits a deuteron, and you make a helium-3 that's going fast, that helium-3 will hit a deuteron, and you'll generate a 17 MeV proton. So in the Kosaki's data, he's got protons here, which are from secondary reactions, where two deuterons have collided, a helium-3 is hit, and it bangs into a deuteron. But in addition to this, he's got this low-level signal here. And this low-level signal is not something which appears obviously to correspond to any normal reaction process. So let's talk about that for a moment. Primary reactions are these, and the reaction products are low energy. The proton is the most energetic of the particles and has 3 MeV. The reactions that make fast protons and alphas are the primary D hits helium-3 already in the target. 2 Ds make helium-3, and this helium-3 bangs into a deuteron to make a proton helium-4 reaction. Now you can calculate the distribution of energies that you would expect in this case. The primary reaction with a low energy deuteron coming in, low energy in this case being 100 kilovolts, that's not very much energy in the grand scheme of things. Because it doesn't have much energy, the associated line width is relatively narrow. For the secondary reaction, the helium-3 that was made has an energy in the neighborhood of 800 plus kilovolts. And 800 plus kilovolts is enough that the proton that you would get out would have an energy spread much greater. However, there is no way that you can have protons from the secondary reactions below about 12 MeV. If you have an isotropic 3D reaction, namely a deuteron hit 2 deuterons at close range, if the reaction were isotropic, then the distribution of the function of energy would be here, so you get stuff around 10 MeV, which is what Kosaki saw. My friend Graham from NRL sent me some view graphs. Kosaki reported the experiment in one facility. He built another facility to Hokkaido University and observed it there under different conditions. It was observed in another laboratory in Japan, it was observed in China, and last year, Graham Hubler and colleagues at the Naval Research Laboratory undertook to replicate the basic Kosaki experiment at NRL. The particle spectra look something like this. I should have things over to grams, but your primary proton, 3 MeV proton peak is here. There's pulse pileup signals here. The secondary reactions are here, and there's a little bit of junk here, a little bit of signal or something there. If blow it up, if you clean it up by putting in an aluminum foil absorber to get rid of some of the initial proton peak, you can see your primary D hits helium-3, which is fairly narrow. Your secondary reaction, which is broader, which sort of corresponds roughly to the curve, that theoretical curve I gave. And then there are some anomalous counts, and the anomalous counts appear to persist as the experiment is made, as is improved. Graham spent like forever, and is continuing to spend forever trying to clean up, to clarify between signal and different noise levels. This result is a function of time. The most recent case, the signal is now in excess of the background, the understood background. Let's think about the yield of the secondary reactions, the products one. The calculated yield for this reaction is around 5 times 10 to the minus 6 as compared to the rate for diffusion reactions. So initial Kasagi measurement is higher than the secondary by something like in the general neighborhood of a factor of 2. The NRL measurements go up to roughly 10 times the signal strength of what you would get if you had the secondary reaction only. So not only is the energy not right, but the amount of signal is not correct as well. Conclusion from the Kasagi experiment. Yield of anomalous signal as large as 10 times the expected secondary reaction. Signal shows up where no secondary reaction is expected. No other reactions are expected in this range as far as anyone knows. But a proposal for a coincidence version of Kasagi experiment, because this is a big result. If it's true, it's the real thing. And if it's true, you'd actually like to see the reaction products appear at the same time. Propose simultaneous observation of the proton and helium-4. If you energy resolve it and angle resolve it, you have the chance of actually proving that this process exists and it works in a way that would be very hard to argue against. So conjecture, it's possible to prove the existence of the, actually it's possible to prove from, for instance, Kasagi, the 2 deuterons are present in the elastin at a small distance. And then the inference is that this infers the presence of the null reaction. For this to be true, if 2 deuterons are close together, if they try to just be stationary at close range, they of course would touch each other, fuse, and that would be that. So you would expect localized states to be very unstable. However, if the 2 deuterons, if they're close, that they have to be spinning around. They have angular momentum. And there's a centrifugal barrier that's formed. And that centrifugal barrier inhibits tunneling. Only the 3 particles would have to tunnel through the centrifugal barrier. You can calculate fairly easily, as a function of the angular momentum quantum number, what the inhibition of the tunneling rate is. And you find with the exchange of something like 20 quanta, 20 units of angular momentum, you've got to have like 35 orders of magnitude in the tunneling lane. So as a result, if you have states, if you have a mechanism to inject angular momentum into your localized states, they'll be stable. So the existence of a Kasagi type signal implying convex states actually implies as well that there's high angular momentum involved in the convex states.
Is this experiment ever been done on palladium deuteride?
Yeah.
Does it give similar results?
Yeah, it gives similar results. Okay, so exchange of many photons can lead to high angular momentum states. High angular momentum states are stable against D diffusion. For a 3-body D hitting 2D reaction, you would also expect suppression of the 2-body exit channels from 3D reaction. So, for example, there's a tritium-helium-3 reaction channel and an alpha-deuteron reaction channel. Those are the 2-body reaction channels, but those would have a very high centrifugal potential to go through, so you wouldn't expect it. And in fact, at least by observations by Kasagi, there's no evidence for these 2-body channels, which is actually quite strong support for the presence of high angular momentum if these things in fact are compact states. Conjecture: compact 2 deuteron states, they exist are high angular momentum states, where high means on the order of 20 or larger. Let me talk a little bit about the theoretical foundation. And at this point, I probably have to begin carrying sleeping people out of the room. But in the nuclear physics community, the early description of fusion reaction processes was done through something called the resonating group method. Wheeler formalized the resonating group method. I suspect he invented it as well, but I'm not sure of that. Basic idea is that you make a wave function that has pieces that describe the nuclei, and then a piece that describes how far apart the nuclei are from one another. You assume that the nuclei are fixed, and you try to get the very best approximation for the description of their dynamics. And to do that, you take your trial wave function, you put it in your Schrodinger equation, you try to optimize the channel separation factors, and you get what's called coupled channel equations. And these equations are what the nuclear physicists use to describe the DD fusion processes from the 1930s till the early 1990s or so. This competes with the closely related R-matrix method, for which everything I'm going to talk about carries over. I'm proposing the lattice resonating group method, and the basic notion is that you'd like to include the lattice at the outset in your theoretical description. So the proposal is to start out with a wave function that's constructed similarly. The nuclear pieces will be the same as we had before. The only difference is here, instead of having just the two-body channels, let me include the rest of the lattice as well. The two-body channels include center of mass coordinates. The center of mass coordinates can be chosen for all the other nuclei as well, and it costs nothing extra other than massive amount of complication in your channel factors to generalize the normal nuclear vacuum description to the lattice. So this is it. This is proposed in 2000. The optimization of the lattice channel factors is done in exactly the same way as for the normal vacuum problem. And this gives you the theory. This is the content of the foundations of the theory that I'm using to work on the anomalies. So if you'd like to believe that, that there's errors in it, this is the place to start pounding on to look for problems with it. Postulate: new physics must result from correct quantum description of both the nuclear and solid state systems. The proposal that I'm making is just simply to combine them. Take your best nuclear description, your best lattice description, combine them together. Time's starting to run short, and I'm starting to get into theory, so I'm likely to, I think it's probably appropriate to do a bit of fast forwarding to focus on some of the conclusions that are important. I proposed a two-site problem as being the simplest possible version of this that you could analyze. And the two-site problem would have helium-4 on one side, 2 deuterons on another side, all deuterons, all helium, and exchange. So you can set up the channels for this problem, and you can work through absolutely everything if you assume simple nuclear models. You still have to deal with the interaction of the lattice with the nuclear, and this is non-trivial. The proposal is that a coordinate for the center of mass of the nucleon, you've got, if you're doing a nuclear problem in vacuum, you care about where the particles are. So the center of mass coordinate is important. If you're in a lattice and you have a highly excited phonon mode, well, the phonon mode is important, and you need to describe that properly. The proposal is to include the phonon mode as well. And whatever's left over basically is a residual local coordinate. So in this way, what's proposed as a way to analyze the interaction between nucleon and lattice in the presence of a highly excited phonon mode. If you do this, you actually can analyze and get an analytic expression for Gaussian interaction with Gaussian orbitals for your interaction, which tells you everything about how phonons are exchanged and angular momentum is generated in these reactions. For this problem, this has been analyzed and understood completely. You generate a couple channel equations, lots of them. So the thing about this formula is that you get lots of coupled equations. And you solve them all, and what you find is that the two-site problem does not give a stable two-deuteron compact state. So you go through all of this, and at the end it says, it doesn't work. And the reason it doesn't work is that the coupling's not strong enough. And then you've only got one site to exchange with. So brainstorm was if you included other sites, and many sites, that the interaction would be stronger. Which has been done. Now, in order to try to get a handle on what things would look like if you included more sites, I made use of something called infinite order Brillouin-Wigner theory, which is in nuclear physics, the projection operator version is also known as Feshbach theory, the Hermann Feshbach, formerly of MIT. If you use infinite order Brillouin-Wigner, you get something like this, and this reads molecular D2 problem and other stuff. And this other stuff reads, take two deuterons, have them come together and make helium-4. Have the helium-4 come apart at another site and give two deuterons. So it's an exchange term. The question is what if you take something really complicated and you want to understand it, you make a simple analog. So a simple analog in this case is a one-dimensional well, which represents the molecular D2. An exchange term near the origin, which represents this new process. And this gives a problem that you can solve exactly. And the claim is that by solving exactly this simple problem, it tells you something about the behavior of the very complicated multi-channel problem described. Now what this simple problem gives, when I saw this I was stunned because I didn't know it was possible, is that this simple problem gives a compact state. It gives a real life new state. Well, it's not a new state. Your Hilbert space has to stay the same, but the states that were present previously combine to give you a localized state. You have a localized state, the energy of which depends on the coupling constant for the exchange potential. These states here are the normal bound states for the well, which represent the molecular ground state versus 6 second cycle. But this new thing here is a compact state, which is localized near the origin. The one-dimensional analog then, in fact, gives what you can identify as two deuteron compact states in the problem. Now, if you look at the molecular state now with this exchange thing, in this case I've chosen to do a reasonably realistic molecular potential problem. What you find out is if there's no exchange, you get a wave function that looks like this. But when you start to turn the exchange on, then your boundary condition changes, and when your boundary condition changes, you start to get a different behavior near the origin. And what this means is that in the presence of a compact state, which is merely resonant with your molecular state, the probability that you can go from here to a small radius now changes dramatically. And that's very, very interesting, because there's always been a problem of how you get two deuterons close together, given that tunneling inward is inhibited. Well, the answer is if you have a compact state, your resonant small r, that changes the boundary condition, that changes what the state looks like. So compact states being a resonant changes the probability. Okay. So Jeff, how much are you going to strangle me for running over? Should I wrap it up? What's the feeling?
Another 5 minutes. You want some time for questions?
Yeah. 2 more minutes. Okay, I went to the generalized to the many-site version of the model. So now we're talking, instead of just 2 sites, or instead of Brillouin-Wigner, we're talking about trying to set up a model that actually has a lot of sites. Now, if you make some simplifying approximation, these couple channel equations are very, very complicated. If you you assume that the sites are uniform, and if you assume that the phonon exchange being uniform is going to project into the same distribution of angular momentum states, then it gives you a problem you have some chance of analyzing and solving. So this again is a reasonable approximation, simplifying limit. The only thing is that you need a formulation that will capture what's going on. The idea is that you start out with molecular states. The molecular states at large distance do this second order null exchange reaction. And then every once in a while, one of these second order null exchange reactions is going to either decay or leave or dissociate or make a chamber-like disintegration occur. So you're going to lose your excitation, you're going to lose your compact states. The proposal is to make a formulation with molecular states as a source for the compact states, and then the states that have to do with the disintegrations, the loss states. Now, if you split up your Hilbert space in this way, you can solve for your intermediate states in terms of the source and in terms of the quantum system with loss. So basically, you get a flow calculation. The idea is that you divide your states into a reservoir of states, where these states would correspond to like normal physics, nothing fancy happening. Now, when the molecular states go through this mechanism into a compact state, occupy the compact states, then the proposals would describe those with an intermediate state as being separate from your source and from your irreversible final states. Here, the proposal is if you lose your excitation by blowing up a Palladium nucleus or doing something else, then your calculation's over. So it's a quantum flow calculation, and the decay channels then show up in this modified Brillouin-Wigner theory as a loss matrix on the same footing with your Hamiltonian. So you can set up models like this and start to solve them. And what you find is that if the coupling is weak and the loss is very strong, if you inject population in at n-naught phonons and with a fixed number, this axis is basically more free deuteron, or more deuterons in this direction, more helium nuclei in this direction. What you find is your intermediate state population doesn't go anywhere. Your molecular deuteron does the exchange thing, makes a compact state. The compact state immediately decays, and there's very little exchange with the lattice and so forth. So this is the case where you don't have very much angular momentum, so states are very unstable, and they don't live long enough to exchange, to undergo this kind of reaction. The idea is that in this case limit, it happens basically once and then blows up. If the compact states were more stable, then you'd have a lot more rattling around the lattice. In this case, I've said let there be higher phonon exchange, which gives you higher angular momentum compact states. And what you find is that you start now to get serious exchange of phonons with the lattice. In this calculation, I've got plus or minus 50 showing up. You also generate large spread of states in molecular or in the nuclear states. So you've got a lot of your deuterons are formed in helium, and a lot of your helium is split apart to make a compact deuteron states. You crank up angular momentum even higher, so the states are more stable, and qualitatively you start to get a really interesting picture. So what happens is that your spread in phonon number now is plus or minus 500. I've calculated this up to about 2,500 on both sides. There's a corridor that forms here where the states are in energy deficit, and there's no loss mechanisms that are allowed. They can't decay. And as a result, what happens is your population tends to channel in this corridor, and there's basically nothing to stop it. And what I find is that the lifetime of compact states just increases by order of magnitude after order of magnitude the more that you populate the corridor here. So all of a sudden now we're starting to talk about a model which gives compact states that can pile up like the Kawasaki states. They start to stabilize. You begin to get large mixing of phonon and nuclear degrees of freedom. And this tempts one to imagine that this model might lead in the direction of heat and cooling production. To address that, I did a calculation in which I said, model calculation, let me have the energy that I'm going to try to exchange be only 500 phonon quanta. Now, either that means that you've got fake nuclei that don't have much energy, or else you've got a very energetic phonon. In this case, the flow starts here with N naught and M naught describing the phonon degrees of freedom, the nuclear degrees of freedom. You see, this line right here is where energy is conserved, where you exchange nuclear energy for phonon energy. In these places where the darks are coming down, these are where you've actually converted one quantum of nuclear energy to an equivalently large number of phonon energy. And so for this restricted model, it's actually now starting to give direct conversion of nuclear energy to phonon energy through the compact states. So the theorem, actually, one thing to follow up on is that a result of these calculations is that within these calculations of any site model, the compact states stabilize. The energy associated with the compact state interaction now is negative, which means it's attractive. This is within the modeling of physics here is a very good result. So the theorem is that stable 2-deuteron compact states now exist in the many-site model. The many-site model has within it now low-level diffusion, the Jones effect. It's got induced disintegration. It's got the Chambers effect. It's got excess heat for helium, so it's got the Pons-Fleischmann effect in it on equal footing now in the same model. It also has tritium, slow tritium production within it, which I'm not describing. This model also appears to give quantitatively, or can be matched quantitatively to the both induced radioactivity spectrum. So it appears now we've finally got a model that's relevant to the anomalies. Anyway, I got a gazillion calculations or conclusions, but I think I'll stop here.
Thank you.
We have any questions for Peter?
Nanoparticles of metals, like polymethyl, are known to have a very different phonon population. And couple that with our Weichmann-Schwarz observation of a change in tritium decay rate by 40%, I think that seems to somehow fit a little bit.
Yeah, I'm not sure that anything I've done is impacted with that. Certainly, I'm aware of the differences in the phonon structure and frequencies for smaller particles. That's interesting. My model actually requires that the deuterons be local in molecular states. Normally, at low temperature, like in deuterite, the deuterium is in the octahedral sites with very little molecular state formation local in the lattice. If you have either defective material or you've got small material that's been formed either as a nodule through co-deposition or through some other process, you have large number of vacancies. Vacancies enhance the local molecular state formation of deuterium inside the metal. So in that sense, small particles or defective particles appear to be very important in this. In non-defective media, in the palladium instant SRI, if you can fill up all the octahedral sites, then you inject extra deuterons, you have a chance of some of those who go 2 per site to make local molecular states. And that seems to be very important for the SRI experiments, which appear only to work with low coordinates of the mid-90s 0.95 fractional occupation. Other questions?
What about the tetrahedral sites at the levels of deuterium concentration at which you get
Right,
maximum effects? The tetrahedral.
You get some occupation in tetrahedral sites. The problem is that you got a saddle point between the octahedral and the tetrahedral site. And the saddle point sort of argues against trying to get them to tunnel together. It's much better if they're in a molecular state in bed in the same site, because you calculate, I've actually calculated in detail overlap probabilities for different site occupations, same site occupation. There's maybe 30 orders of magnitude difference for same site occupation.
The other question related to the phonon models, have you, if you include anharmonicity in the vibronic, could that be a substitute for going to many sites?
The way I view that, there's two important effects. One is that your oscillator, because of that harmonicity, isn't an oscillator, harmonic oscillator anymore. And I've actually calculated this physics in the presence of non-harmonic oscillator. The answers are essentially the same. You don't get much difference at all. The other issue is that if you have anharmonicity, then you can begin thinking about driving an acoustical phonon mode very strongly. That couples to an optical phonon mode that has some fractional occupation. Optical phonon mode. The optical phonon mode can bring the deuterons closer together, which is what you need to establish a matrix on. So anharmonicity extends the frequency range over which you can have the possibility of having an interaction. So in that sense, that's very important.
Yeah, because actually, again, experimentally, anharmonic, hydrogenic, and deuterium modes have been identified.
Right, of course.
At those frequencies.
The local deuteron frequencies is measured by slow neutron scattering. Shows a very anharmonic local potential.
Here, you're presupposing two deuterons close to one another. How many of these things do you need? How close do you have to be?
Actually, the calculations are starting to give those numbers.
You say many sites, what's that mean?
Well, here, I can actually start reading off here. I've done calculations where I've had like 2 or 3 sites now with compact states of helium talking to a single phonon mode, and I get Jones type effect things. Turns out I need something like 12 or 15 deuteron pairs interacting with a single phonon.
How far apart are they?
Well, your optical phonon mode, if it's lossy, is probably in the order of 1,000 angstroms or less. People struggling if I got the number wrong there.
The last question.
If there's gain that can be bigger, if it's acoustical, it could be a little bit larger. If the loss is less, it could be a little bit larger. But if you got like a dozen inside the 1,000 cubic angstrom region, then this physics should turn off. But that's
angular momentum.
In the modeling of the nuclear interaction, including phonon exchange, I get an analytic form.
You're saying the lattice is causing this?
No, on a microscopic scale, you've got the 2 deuterons, which are, in the absence of phonon excitation, they tunnel together. And you picture them tunneling together, so they're kind of like sitting next to one another with this quantum mechanical spreading, tunneling going on.
Within 10 Fermi or something really close?
Well, you can have, theory says you can have 0 overlap, aside from probably, forbidden exclusion, Planck exclusion principle. But there's no reason. I mean, the overlap probability of 10 Fermi and 0 Fermi, within 20% of one another or something for 2 deuterons. So the picture is that you somehow managed to tunnel somewhere together. Now, the lattice is very highly excited, and the 2 deuterons can be thought of as part of the lattice. If your lattice phonon is very highly excited, what that means is your 2 deuterons are going to have a small response that's consistent with your lattice excitation. And you can use local linear response theory to calculate the response of your 2 deuterons locally at short range to include the effect that the phonon mode has on them. And that's where the phonon exchange probability comes from. Because that motion now, the relative motion, a very tiny varying scale, incremental motion that these things have being driven by the lattice, that contains angular momentum. In fact, the amount of angular momentum contained in the motion, the amount of potentially available angular momentum is actually zillions of units. However, if you calculate things out according to the exchange model that I've worked out, you actually need something like a couple of Fermi's motion before you can exchange 10 phonons. So, we're starting now to get numbers of correspond to response to actual microscopic distance with the phonon motion has to cause these things to move in order to exchange enough phonon quanta to generate nothing.
So we have a chicken and egg problem here.
I don't know if it's a chicken and egg problem.
These things are able to recite phonons.
But what it means is that if you're either got acoustical phonons, which aren't effectively exchanging phonon nuclear interaction, or you got optical phonon excitation that's not too strong amplitude, then the amount of motion locally is very small, which means that you can only exchange a couple of phonons, period. And if you exchange only a couple of phonons, then your initial molecular state is helium-4. Helium-4 projects into unstable compact states. So these things live for 10⁻20 seconds.
So how do we get the state?
You have to get your phonon lambda, an
How do you
optical.
get the stable? How do you get the phonons? Get stable.
If you were in a lab and you had a terahertz source, you might shine the terahertz source on the surface and generate it.
What are we doing when he's getting the stables?
In McCouvery's experiments and many other people's experiments, if you drive a flux of deuterium inside the lattice down a chemical potential
You're saying the
that's
flux.
50 millivolts or more, the flux of deuterium down a chemical potential, sudden discontinuity, is the most efficient way of generating optical phonons that I can think of. There is no method more effective for generating optical phonons than that. In the current generation experiments, the Eilenberg experiment, the recent Newton experiment, all of McCouvery's experiments, Smiley's experiments, all now have a recognizable deuterium flux component.
Maybe take one more question, and then people can stay a little bit, and let the general audience go. If anyone wants to stay with Peter, as long as he's willing to stay.
Kind of a practical question. So if your null experiment, the hypothesis is correct, I mean, just as kind of an experimentalist, I would take that back to my lab and say, well, if I shoot some, if I send an alpha source in here, or I load my rod up with helium-4, I should see some sort of enhancement? Or is there any kind of other experimental gain?
There are other experimental handles. If you, again, these curves tell you how many helium-4 you want to have present inside of a phonon node. And the numbers come out that you'd like to have at least on the order of parts per million helium to satisfy having a few within an optical phonon domain. So if you starve it for helium-4, if you have an experiment that otherwise gave you a result, and then you set up a version of it that was starved with helium-4 but didn't have enough to make this work, and you could not produce stable Kazaki states, and that would be a way of shutting things off. So there should be sensitivity to helium-4, but I think it's one which says that normally metals come ubiquitous helium-4 concentration from atmospheric input and from the helium present when they were first cast. So as a result, your normal slug of metals got enough helium-4 to support this. And if you add more, this corridor thing, if I add more helium, doesn't seem to change very much, at least for the better. So you can make it worse by restricting it. I think you can also make it worse by putting in too much.
I think we should thank Peter again, and anyone who wants to stay.
Yeah. I want to ask a few more questions. I'll tell you.
Anyway, so that's one way to
Well, basically,
No, I don't understand the whole concept.
And so anyway, we're in the process of finalizing that deal now. We've had some conversations. So this would be working with Molly.
So I guess the hours
No, she still wants to do that. She's just not grand. And we also have some interest in but my choice, it's one of these like business choices. Thing is, I like the Nova idea a lot. As, first of all, they're here, although the is probably in Hollywood. Having the Nova branding gives it a kind of.
How does a Nova brand just because?
Well, he and her producers, but again, but it's a very good thing for his episode. There's nothing in the future to actually say. Basically, what we've done, we take the camera.
Her husband.
Although it is patterned very clear for legal reasons.
Is she interested in just your experience? Did stop to